In theoretical physics, the BPST instanton is the instanton with winding number 1 found by Alexander Belavin, Alexander Polyakov, Albert Schwarz and U.S. Typkin. It is a classical solution to the equations of motion of Yang-Mills theory in Euclidean space-time, meaning it describes a transition between two different vacua of the theory. It was originally hoped to open the path to solving the problem of confinement, especially since Polyakov had proven in 1987 that instantons are the cause of confinement in three-dimensional compact QED. This hope was not realized, however. Description: the instanton, the BPST instanton, is an essentially non-perturbative classical solution of the Yang-Mills field equations. It is found when minimizing the Yang-Mills Lagrangian density, with f mu nu a equals mu a nu a nu a mu a plus g epsilon a b c a mu bar nu c. The field strength. The instanton is a solution with finite action, so that f mu nu must go to 0 at space-time infinity, meaning that a mu goes to a pure gauge configuration. Space-time infinity of our four-dimensional world is S3. The gauge group SU has exactly the same structure, so the solutions with a mu pure gauge at infinity are mappings from S3 onto itself. These mappings can be labeled by an integer number q, the Pontryagin index. Instantons have q equals 1 and thus correspond to gauge transformations which cannot be continuously deformed to unity. The BPST solution is thus topologically stable. It can be shown that self-dual configurations obeying the relation f mu nu a equals plus or minus 1/2 epsilon mu nu alpha beta f alpha beta are minimize the action. Solutions with a plus sign are called instantons. Those with the minus sign are anti-instantons. Instantons and anti-instantons can be shown to minimize the action locally as follows, where the first term is minimized by self-dual or anti-self-dual configurations, whereas the last term is a total derivative and therefore depends only on the boundary of the solution. It is therefore a topological invariant and can be shown to be an integer number times some constant. The integer is called instanton number. Explicitly, the instanton solution is given by with z mu the center and rho the scale of the instanton. Eta mu nu is the T-Hooft symbol. For large x2, rho becomes negligible and the gauge field approaches that of the pure gauge transformation. Indeed, the field strength is and approaches 0 as fast as r-4 at infinity. An anti-instanton is described by a similar expression, but with the T-Hooft symbol replaced by the anti-T-Hooft symbol, which is equal to the ordinary T-Hooft symbol, except that the components with one of the Lorentz indices equal to 4 have opposite sign. The BPST solution has many symmetries. Translations and dilations transform a solution into other solutions. Coordinate inversion transforms an instanton of size ρ into an anti-instanton with size 1 ρ and vice versa. Rotations in Euclidean four-space and special conformal transformations leave the solution invariant. The classical action of an instanton equals, since this quantity comes in an exponential in the path integral formalism, this is an essentially non-perturbative effect. As the function e-1 x squared has vanishing Taylor series at the origin, despite being non-zero elsewhere. Other gauges. The expression for the BPST instanton given above is in the so-called regular Landau gauge. Another form exists, which is gauge equivalent with the expression given above, in the singular Landau gauge. In both these gauges, the expression satisfies mu a mu equals 0. In singular gauge, the instanton is in singular gauge. The expression has a singularity in the center of the instanton, but goes to 0 more swiftly for x to infinity. When working in other gauges than the Landau gauge, similar expressions can be found in the literature. Generalization and embedding in other theories. At finite temperature, the BPST instanton generalizes to what is called a caloran. The above is valid for a Yang-Mills theory with SU as gauge group. It can readily be generalized to an arbitrary non-abelian group. The instantons are then given by the BPST instanton for some directions in the group space, and by 0 in the other directions. When turning to a Yang-Mills theory with spontaneous symmetry breaking due to the Higgs mechanism, one finds that BPST instantons are not exact solutions to the field equations anymore. In order to find approximate solutions, the formalism of constrained instantons can be used. Instanton gas and liquid. In QCD it is expected that BPST-like instantons play an important role in the vacuum structure of QCD. Instantons are indeed found in lattice calculations. The first computations performed with instantons used the dilute gas approximation. The results obtained did not solve the infrared problem of QCD, making many physicists turn away from instanton physics. Later, though, an instanton liquid model was proposed, turning out to be more promising an approach. The dilute instanton gas model departs from the supposition that the QCD vacuum consists of a gas of BPST instantons, although only the solutions with one or few instantons are known exactly. A dilute gas of instantons and anti-instantons can be approximated by considering a superposition of one instanton solutions at great distances from one another. T. Hooft calculated the effective action for such an ensemble, and he found an infrared divergence for big instantons, meaning that an infinite amount of infinitely big instantons would populate the vacuum. Later, an instanton liquid model was studied. This model starts from the assumption that an ensemble of instantons cannot be described by a mere sum of separate instantons. Various models have been proposed, introducing interactions between instantons or using variational methods endeavoring to approximate the exact multi-instanton solution as closely as possible. Many phenomenological successes have been reached. Confinement seems to be the biggest issue in Yang-Mills theory, for which instantons have no answer whatsoever. In electroweak theory, the weak interaction is described by SU, so that instantons can be expected to play a role there as well. If so, they would induce baryon number violation. Due to the Higgs mechanism, instantons are not exact solutions anymore, but approximations can be used instead. Due to the non-perturbative nature of instantons, all their effects are suppressed by a factor of E-16 pi squared per gram squared, which, in electroweak theory, is of the order 10⁻179. Other solutions to the field equations. The instanton and anti-instantons are not the only solutions of the Wick-rotated Yang-Mills field equations. Multi-instanton solutions have been found for Q equal to 2 and 3, and partial solutions exist for higher Q as well. General multi-instanton solutions can only be approximated using the Valley approximation. One starts from a certain ansatz and one minimizes numerically the action under a given constraint. Solutions which are not self-dual also exist. These are not local minima of the action, but instead they correspond to saddle points. Instantons are also closely related to merons, singular non-dual solutions of the Euclidean Yang-Mills field equations of topological charge 1/2. Instantons are thought to be composed of two merons.